So it's our great pleasure to welcome today Doug Lenat from Sci-Corp. Doug, as many of you know, is one of the leaders in the field of AI, one of the original fellows of the AI Association. I remember reading about his automated mathematician program in 1976, and it was one of the things that really inspired me to go into the field. And Doug has really been sort of had a consistent vision and leadership in this field of sort of common sense knowledge representation. He's been the Moses of the field, striving to write down the knowledge in the book. Since then, you know, things have evolved and changed, and in terms of connecting the most people with their queries to knowledge, I guess Google has taken over the field of being the mountain in terms of answering the most queries. But today, Moses has come to the mountain, and we reverently listen to what he has to say.
Thank you, Peter. Thank you. That was an amazing introduction. So as you could tell, we had some audiovisual problems, so the various demos and so on that I was going to show you, I won't be able to, but after the talk, if you're interested, come on up to the front, and on a very, very small screen, you'll be able to see some of this stuff running live. But the PowerPoint presentation is almost as good. So basically, I had a meeting with Vint Cerf recently where he encouraged me to use the word relevance as much as possible in this talk. So really what I'm going to talk about today is semantically determined rather than syntactically determined relevance. The basic problem is that even after 50-some years, software is still incredibly brittle. If you talk to medical diagnosis systems, even if they're world-class diagnostic experts, as a joke, we told the system about my old rusted-out Pontiac, and you know, it asked questions like, are there spots on the body? Yes. More on the trunk than elsewhere? No. What color? Reddish-brown. Diagnosed it as having measles with a very high confidence level. Or car loan approval system which granted a loan to someone who put down that they had 19 years of on-the-job experience at their last job, even though they were less than 19 years old, and so on. I could go on, but you sort of have all these examples yourself from your everyday life of this kind of brittleness of software. In terms of Google, you get queries all the time, like this one, which if you basically type this into Google, you won't actually get the answer in any one place. And it's heartbreaking because, of course, there are lots of places on the web that have one or the other of these building heights. In fact, there are a lot of pages that have both of the building heights. And because they just happen not to have a sentence of this form, they're not going to give you the answer. They essentially would make you get the answer yourself by doing the arithmetic yourself. Or if you have a query like this of some movie to take the kids to nearby here that's starting soon, why should you have to go to 2 or 3 or 4 different sites in order to put the information together to get the answer to a query like this? By the way, this was in case you were dubious about the fact that you couldn't answer that query. The first hit actually seems to answer it, but it turns out they're talking about replicas of these objects in Las Vegas, not the not the actual originals and so on. Now there is actually a page you can go to and get the height of one and the height of the other, and so if you're able to do subtraction, you can get the answer to your question. So really what I'm talking about here are a combination of missed opportunities where the software doesn't really understand what the user is asking and can't combine information across pieces of software that have been written, so that even if someone writes a program which is able to answer a certain kind of question, you can't just dump all those programs together and have them be as smart as someone who had all those capabilities. There's a real danger and an increasing danger in this kind of brittleness, namely as programs get more and more power in the real world, you're giving power to what are in effect idiot savants. You wouldn't really take your child to a physician who was an idiot savant who didn't understand that automobiles can't get measles and so on. Similarly, every 20 years or so, there's a surge of sort of a media frenzy about forthcoming home robots You may remember 20-some years ago it was Nolan Bushnell and Andron, but now there's partly because of the Roombot and so on, you see lots of articles now about the impending home robots that will mind the baby and mow the lawn and so. Well, the trouble, of course, is that they'll just as blithely mow the baby because they don't know, they don't care, they don't have common sense. Programs have the veneer of intelligence at most, not true intelligence. And sometimes when they have the veneer of intelligence, they're even more dangerous than when they don't. To give you an example of what I mean by the veneer of intelligence, we could go back 40 years to the ELIZA, or doctor program, that Joe Weizenbaum did at MIT, back when Rogerian psychology was very popular. This is sort of reflection. So you say things like, I smoke, and it says things like, tell me more about the fact that you smoke. So one of my favorite examples was where we said, my dog's mother died recently, and the program said, tell me more about your mother. Now, the less you know about computer science, the more deep this psychiatric insight really appears to be. Mostly what's going on here is that the program simply doesn't know the word dog. So it sort of hears blah, 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 mother, and then it says, tell me more about your mother. This is a lot like the Gary Larson Far Side cartoon that you may have seen, where it's like this guy is talking to his dog, and it's like what he says and what the dog actually hears. And for those of you who are dog people, I will show you the rarely seen cat version of this, of what you say to the cat and what the cat hears. So basically, fast forward 40 years, and you say, well, surely in 40 years we can do a lot better job than that. Well, it turns out if you look at the Turing test competitions that go on, they're still won by these annoying little chatbots like Alice, where you say, like, what is the color of a blue car? And it gives you back some garbled ELIZA-like version of that. Or you say, I'm going to ask you some simple questions, and it says, like, do you think your plan will succeed? Or where is Sue's nose when Sue's in her house? And it says where it belongs. Now, this is actually not such a bad answer, but it then ruins it by going on to say, try searching the World Wide Web. Anyway, obviously, if you go to Encarta and ask that, you get some garbled, well, actually, in this case, you get 2 hits, one on the history of automobiles, and then one, I guess, because it doesn't understand capitalization and punctuation, on the Central African Republic. If you go to Ask Jeeves, you pretty much get the same results that you'd get from Google, namely pages that happen to mention those words, but not actually understanding the question. So the basic idea is, can we get the computer to understand semantically, not just syntactically, not just store information for portrayal and depiction and presentation to human beings, but actually understand the questions that are coming in, actually understand the material that it's displaying and searching through and indexing, to reason to decide what's relevant, and even better, to reason to decide how to arithmetically or logically combine information from 2 or 3 or 5 different sources to answer a query that isn't answerable on any one single page anywhere. So, okay, let's go about telling the computer all the sorts of things that you know about cars and colors and the Eiffel Tower and heights of buildings and movies and so on. And there's actually a lot of stuff that people know. But still, we could write that stuff down and tell it to computers. So here's a couple sentences about kitchen appliances. Now, after you say this, does the system understand that microwaves and dishwashers are kitchen appliances? Well, not really. I mean, it has those sentences, and if you ask it in just the right way, it'll tell you yes, it understands that. But really, for all intents and purposes, we could have typed this in because it doesn't really know what the terms mean. So you could say, well, we need to tell it more about each of these kinds of things. Well, this first thing requires electricity, and the second one requires electricity and water. Well, but remember, it doesn't really know English, so it doesn't know the meaning of those terms. So you have to tell it more about those things, like Buzzqua is shipped to people's houses in liquid form through pipes, and so on. You keep on doing this again and again and again, keep explaining the meaning of these terms, and not just the terms, but also the relations, like requires. And slowly, this converges. Slowly, it converges after writing millions and millions of these assertions, into a set of axioms that have only one model, namely the real world. And finally, when you've written enough, you can believe that the conclusions that would deductively come from all these assertions would be the same conclusions that you would believe about things in the real world, like pipes and water and liquids and heights of buildings and so on. So to bring this home to you guys, how do I think the results that you present could be more relevant if the search engine had some sort of understanding? And I've actually included here, for old time's sake, some examples that were motivated by people in the audience, in some cases actually implemented by people in the audience 5, 10, and in this case 15 years ago. This is something that R.V. Guha worked on when he was working on our project. So here someone is asking for pictures of someone smiling, and the psych system was able to come up with a match on this particular captioned image, a man helping his daughter take her first step, where obviously none of these words are synonyms, so syntactic matching is not going to find this particular match for you. But on the other hand, as a human being, you understand things about the real world, like when you become happy, you smile, and when somebody you love accomplishes something, it makes you happy, and taking the first step is an accomplishment, and parents love their children. And so if you believe these things, then it's a fairly short deductive proof to decide that this image is likely to be relevant to this particular caption, i.e., this image is relevant to this particular query, rather, that this image probably depicts someone who is smiling. And so Psych has these pieces of knowledge. They're represented in some machine manipulable formal language, basically predicate calculus form. And so we're talking about a 3 or 4 step proof to decide that this query and this caption actually unify. So if you have these pieces of knowledge, finding this match is trivial. If you don't have these pieces of knowledge, finding this match is impossible. It's not like you could add another 15,000 servers or let your algorithm run another 5 seconds and it would find this match. It'll never find this match without these pieces of knowledge. Here's another example from the R.V. Guha days, where the query was for pictures of strong and adventurous people, and the entire document here is a caption of just half a dozen words, a man climbing a rock face. And you have to know things like, when you're doing rock climbing, you have to repeatedly lift your own body weight, so you have to be at least moderately strong. And if you put yourself at risk of dying like this, then you have to be at least moderately adventurous. And again, we're not talking about beating Kasparov at chess, doing 37 deep reasoning. This is a trivial kind of search if you have those pieces of knowledge and if the computer is able to use those to mechanically manipulate those to do deductions. There's nothing special about image retrieval. One recent example from a project we're working on for the government was an analyst query for government buildings damaged in terrorist events in Beirut during the 1990s. And the actual document talked about a 1993 pipe bombing of France's embassy. And so you have to know things like embassies are government buildings, and 1993 is during the 1990s. And if there was a pipe bombing, then probably it was a terrorist event, and so on. So again, knowing a few things about the real world, you can answer this query. Sometimes you need domain-dependent knowledge as well. Like to answer this one, you have to know things like SA-7s are capable of shooting down low-flying aircraft and so on. But you get the basic idea. We're talking about relatively short, relatively simple searches if you have the pieces of knowledge. So this is a little thank you to Guha for pushing us in this direction. Not just finding information, but also consistency checking, and in some cases guessing at missing pieces of information can be done this way. So here you can think of this as an Excel spreadsheet or a relational database of employee information. And in this second row, we see things like, well, this person looks like they were hired before they were born, and they listed themselves as their own emergency contact, and the person that listed them as their significant other is different from the person they listed as their significant other, and so on. And so this doesn't violate the data type of this particular data structure doesn't violate the constraints, let's say, of the spreadsheet, but it violates common sense. It violates your knowledge about the everyday world, and human attention should be called to this. And you could say, well, why isn't it the responsibility of whoever put this together? Why, when they were putting this schema together, why didn't they preconceive all the different constraints? Well, in reality, there aren't 8 columns, there are 80,000 columns, and they're not spread over one single table, they're spread over hundreds or even thousands of tables, and the people who put those databases together had no idea of the existence of each other. And it's your ability to read the column or relation headings and understand what they mean in human terms, in common sense terms, that enables you to decide that some of these things are contradictory with each other. So how can our programs be intelligent rather than just having the veneer of intelligence? And the answer is by having and by being able to apply, not just store and display, this large corpus of knowledge spanning pretty much everything from domain-dependent knowledge to what you would call common sense that Og the caveman had, like if you've got some open container of liquid and you turn it upside down, the stuff's going to fall out. Basically, I could go through lots of different examples from lots of different subfields, but partly because of Peter and some of the other folks in the audience here, I chose some examples, poignant examples from natural language understanding to drive that point home of why you really need to have this kind of knowledge if you want to semantically understand, not just store and display this kind of information. So here's, and a lot of these examples are actually 30 years old from a class I took from Terry Winograd at Stanford back in the early 70s. But basically, here's one where you know that the first kind of pen is probably a writing implement and the second one isn't. But what tells you that? Is it the definition of these words? Is it linguistic theory? No, it's your knowledge of how big they are and where they usually are and stuff like that. Or here, the police watched the demonstrators because they feared violence, or the police watched the demonstrators because they advocated violence. One of the theys is going to be the police, one of the theys is going to be the demonstrators, but how do you know which is which? The referent of that pronoun is basically determined in your mind by your model of police and demonstrators and what they do and the context and so on. Mary and Sue are sisters. If I say this to you, you probably assume I mean that they're each other's sisters, not that they each just have a sibling and they're not related to each other. It would be cruel and misleading if that's what I meant. On the other hand, if I say Mary and Sue are mothers, it would never cross your mind for a second that they're each other's mothers. You know, and why is that? Well, it's because of your knowledge of biological reproduction. It's not the English language or linguistic theory that tells you this. Or every American has a mother, obviously not the same mother, but an almost identical sentence, it is more or less the same president. John saw his brother skiing on TV. The fool didn't have a coat on. Who's the fool? Presumably the person skiing. But it's your knowledge of skiing and climate and weather and how televisions work that enable you to determine that. If I had said the fool didn't recognize him, now the fool would be John, the person watching television. Again, your knowledge of the real world helps you to disambiguate these possible reference. I could go on and give you lots more examples, but just one final example. Almost every Burns and Allen routine is built around this kind of misunderstanding. So here's one where George is saying, my aunt's in the hospital, I went to see her today and I took her flowers, and Gracie says, that's terrible, you should have brought her flowers. And that's because there are a lot of words like took and sanction and table that actually reverse their meaning depending on the context in which they're used. And we rely on our knowledge of the world in order to tell us what is actually being intended by the speaker or the author. So when I talk about a large corpus of knowledge, what is this knowledge? We're talking about facts and rules of thumb and so on, but we have to represent this in some fashion that the machine can manipulate. And so by using logic, by using predicate calculus as our representation, computers can do deductive reasoning and incidentally inductive and abductive reasoning as well themselves on that represented knowledge. And because the words are composed of sentences, the sentences are composed of words, the full list of words or terms that we use in our language is something we refer to as the ontology. And because the grammar and the syntax is formally regulated, we can refer to this as essentially a formal ontology. So when people talk about a formal ontology, this is pretty much all they're really talking about. A restricted set of terms and a restricted set of grammar rules for how you can compose sentences out of this, and hopefully restricted enough that the machine can logically create valid deductions out of all this. It's useful to organize terms in your ontology in a kind of hierarchy or taxonomy. That gives you the power of generalization, the power of inheritance. So you can say things about vehicles or trucks or whatever, and some particular truck down here will inherit all that information. Things like, this truck is probably driven by a trained adult human being and probably can't control its altitude. And that kind of taxonomy can also help you to correctly place information. So if you say water vehicles slow down in bad weather, you look around at the neighboring parts of the ontology and you say, well, that really applies more to surface water vehicles, and it really applies to surface vehicles in general. So even though you didn't have trucks in mind when you wrote that rule, it now applies to trucks, and in particular to this truck over here, that the system will understand that that truck will probably have to slow down in bad weather. So you sort of get the idea of using the ontology to help the system figure out, and to help the human building the system figure out where knowledge should be attached. When I say that we want to represent knowledge in logic, obviously you know what I mean by representing knowledge in English. These are ways of representing in a simple predicate calculus notation that Socrates is man or that men are mortal. These are just two alternate ways at different levels of verbosity of saying that men are mortal. You can go on and write more and more complicated expressions to represent things like everybody has a mother who's a female of their species, and so on. Often what we do in a case like this, if we see the same kind of form occurring again and again and again, is we introduce a new predicate, in this case relation all exists, so that what used to be a complicated looking rule is now a ground atomic formula, in this case a simple ternary assertion in our language. So slowly the number of relations, the number of predicates, has increased to about 16,000 in Psych. That number is slowly increasing, especially as we add new domains. But we increase that number kicking and screaming, not because we want to be able to say that we have a large number of different relations. And what do I mean by the system can produce deductions? I mean that just like you would expect a human being in this case to conclude that Socrates is mortal, given that Socrates is a man and men are mortal, if we ask our system, is Socrates mortal, it should and will come back and say yes. And if you ask for the justification, it'll give you exactly the two-step justification that you would expect here. If we had our live demo running, I would show you some cute examples. We have about 50,000 common sense tests that we try to run every night just to try to make sure that the system keeps consistency. One of them is something like can a can. And if you ask that, it'll say no. And if you ask why, it'll say because cans are inanimate objects, and doing the can generally requires at least a partially mental doer as the motive force behind the action, and so on. And similarly, oh, good. We can actually show the one of the ways that this would actually be asked, and one of the forms in which the argument would come out. Here you see the justification in predicate calculus. You can press a button and the system can generate mediocre English, understandable but by no means English we're proud of, to translate these predicate calculus assertions into English assertions like inanimate objects can't be the doers of partially mental events, and cans are inanimate objects, and can dancing is at least a partially mental event, and so on. So you get the idea. And in terms of more complicated examples, we have something that we call the analyst's knowledge base, which intelligence analysts use to answer questions like, were there any attacks on targets of symbolic value to Muslims since 1987 on Christian holy days, or things like that. I think I'll skip through some of that, but you can get the idea. Here's an example where the analyst is asking who had a motive for the assassination of Rafiq Hariri, and they type short phrases in that get parsed well enough, that get recognized well enough, that novices who aren't familiar with Psych and its ontology and AI and predicate calculus can still get their question formed in a way that both they and the system believe it understands. And then when you ask the question, you get various answers, some of which are surprising, like in this case, the U.S. and Israel being behind Hariri's assassination. And if you ask, like, for the sources there, it turns out, well, this is actually some editorial that appeared on Al Jazeera, and obviously, if you want, you can click over to the original source for that one. If you look at a more traditional Western answer, like Syria was behind Hariri's assassination, you can ask for the justification there. And basically you get something which says, well, Syria opposed Lebanese economic reform, and we think Hariri advocated Lebanese economic reform. It's in blue because the system isn't sure about this. This is a kind of abductive reasoning. And if you ask whether or not this is true, the system will generate a kind of augmented query, hand it to Google, and you'll find a set of articles, in this case 19 hits, all 19 of which are actually perfectly adequate for answering the question, was Rafiq Hariri an advocate of Lebanese economic reform? To take an even simpler example, if all you want are articles about his assassination, if you go and essentially type in that to Google, putting in different forms of the word assassinate and assassination, you get some large number of hits, but there are a fair number of false positives and negatives in the results that come back. To see some examples of false negatives, we basically had Psych use knowledge that it had about his assassination, like the fact that it occurred as a car bombing while he was traveling in a motorcade. So you put in some of those terms and you actually get more hits, thousands more hits than you got before. And so there are really large numbers of false negatives that were simply missed by the previous query because they happen not to use the word assassinate or assassination. Similarly, to see some of the false positives, Psych knows when the assassination occurred, and in particular, it knows enough about causality to know that articles that came out years before the assassination are probably not about the assassination. In this case, it's a statement Hariri is making about assassination many years before he himself was assassinated. This was a hit that was among those returned earlier. Anyway, I could go on, but in this particular audience, I'm loath to talk too much about removing positive and negative errors because probably everyone in this audience knows a little bit more or a lot more than I do about that subject. By the way, I want to thank Joel Truer for pushing us in this direction several years ago. That's partly also how we met Michael Whitbrock, who's with us now as our VP of Research. Joel came to us when he was at Hotbot and actually came to us with this really cool idea of taking ambiguous queries like this one, and I'm sure you can return the hits right away. In this case, about 26,000 hits got returned. But there's a mixture of hits about veterans and veterinarians and other things involving motorcycle race veterans and so on. And just ask a query, and if the user happens to click on one of these, like the user happens to click on military veteran, then go ahead and augment the query and ask it, in this case to Inktomi, with ors and not terms to basically hopefully eliminate the unwanted veterinarian hits. And indeed, in this case, you get hundreds of thousands, not tens of thousands of hits, and they're all about veterans. And similarly, if you had clicked on this one, then you'd get the symmetric augmented query. And again, you'd go from tens of thousands of hits to hundreds of thousands of hits, and they'd all be about veterinarians. And the other idea that Joel had, which was a good idea, was use the understanding of the query to suggest plausible follow-up queries. So you wouldn't ask for things, you wouldn't suggest follow-up queries like, how do I train to become a veteran? And so on. So you basically get the idea there. Now, some of the queries that I showed you, like this one, basically require not just common sense knowledge, but up-to-date database type knowledge, the kind of knowledge you might get by visiting a website, in this case a theater listing website, or a Google Maps website, or the IMDb database website, and so on. So how do we get that knowledge accessed via the Psych system as well? So this is really another kind of application of Psych to access structured semantic knowledge in databases and websites out there online. Here's an example in which someone was asking how different in age Qusay and Uday Hussein were. For the sake of argument, let's suppose that one structured source contains information about one brother and one structured source contains information about the other brother. And obviously, using arithmetic and common sense, you as a human being could put these pieces of information together. And Psych, because it knows things like objects age 1 year per year, can also answer this question. And basically, in the case of this question, come up with 2 years as the answer. But more than that, it can come up with 1966 over here, add it to this database, and put as the source this number 30 over here. And it can put the number 32 here and put as its justification this number 1964 over here. Then you can do something cool, which is to throw away Psych entirely, and now you have these augmented structured sources that contain information they didn't contain before, so they're a little bit more complete than they were before this process happened. Here's an example that occurred more recently than the one I just showed you, in which analysts were asking Psych what cities were particularly vulnerable to anthrax attacks. And you have to know things like the number of suitable zoonotic hosts residing near each large city in the US. And if you're not careful, you add things like the number of chickens and the number of pullets, and you get a wrong number, because if you don't know that pullets are a kind of chicken, then you accidentally add them together, that sort of thing. By the way, in case you wonder, the answer is the lucky winner today is Phoenix, and it's basically because Phoenix is warm enough and it has enough people, and it has some astonishingly large number of animals living near Phoenix, and some horribly small number of hospital beds per resident in Phoenix, and so on. So that makes it particularly good target for anthrax attacks. And if you ask why Philadelphia is unsuitable, it's because Philadelphia was too cold on the day we ran this, and so on. It's worth mentioning that there is no one correct monolithic ontology. A lot of times people mistake the Psych effort as trying to claim that there's a single correct monolithic organization of knowledge, set of knowledge to tell the system about. That's really not the case. Psych's axioms are divided into a vast number of locally consistent contexts, or what Guha called micro-theories. And you can think of different attributes like time, things true at one time and false at another, things true at one level of granularity and false at another. So you end up with apparently, superficially, contradictory statements, or things believed by one group and not believed by another, like who killed Rafiq Hariri and so on. If you didn't allow for this kind of local consistency but global inconsistency, you'd quickly never be able to accommodate something as inherently inconsistent as the human mind, let alone humanity's World Wide Web. There is a single correct monolithic reasoning mechanism, namely theorem proving, but in fact it's so deadly slow that really if we ever fall back on our theorem prover, we're doing something wrong. By now we have over 1,000 specialized reasoning modules, and almost all the time when Psych is doing reasoning, it's running one or another of these particular specialized modules. For instance, TVA, which is transitive via arg, that was used in the CanCan, is used for rapidly answering questions that involve transitive relations and graph searching on transitive graphs of relations and so on. It's also worth mentioning that almost everything in the system is true by default, not absolutely true. You can later learn things that will cause you to disbelieve something that you used to believe after all. So we reason by argumentation. We gather up pro and con reasons why we believe or don't believe something, and let different meta-level heuristics, if necessary, decide whether the system should believe something or not. There are also cases where an analyst or a typical user will want the pro and con reasons. In this case, who was behind a certain event, or whether Bill Clinton was a good president or something. There is no single right answer. There are pro and con arguments in each case. A lot of times people ask me things like how many predicates and concepts and assertions are there altogether in the knowledge base. And so I have a slide like this to forestall those questions, but really this is a red herring and you shouldn't really care about these numbers. To give you an example of why you shouldn't, a small number of what we call sibling disjoint assertions in the knowledge base take the place of billions of class-level disjointness assertions and really hundreds of trillions of instance-level non-set membership assertions. So like, if we have a question like, is any seagull also a moose? Now, Cyc should and can answer this question. By the way, the answer is no. And if Cyc knows, let's say, 10,000 kinds of animals, that means there are about 100 million questions like this it ought to be able to answer. So option 1 is we could add 100 million assertions to the system. Then we could change this number to 103 million. It would look really more impressive. But we're not here to look impressive. We're here to do as much as we can with the smallest number of axioms, like piano did. Having 5 axioms for arithmetic is really impressive. So option 2 is we could basically add 50 million disjoint with assertions and one single assertion that says disjoint with is symmetric. A better option is to add 10,000 Linnaean biological taxonomy assertions and one single sibling disjointness assertion, which basically says if you've got any 2 taxons and you don't know that one is a specialization of the other, assume they're disjoint. So if you don't already know that seagulls and mooses, one of these is a specialization of the other from those 10,000 assertions, just assume that they're disjoint taxons. So that's a really good rule. And with these 10,001 rules, you can answer those same 100 million queries. Or depending how you look at it, like, was Bullwinkle a seagull? You can answer hundreds of trillions of queries. Okay, so you get the basic idea. I don't have time to go into detail of what's in the knowledge base, but just to give you the rough flavor of a few things that are in there, we have dozens of ways of talking about the way that something that exists in time relates to something else that exists in time, like starts after the start of. And using those kinds of relations, you can tell the system things and get the kind of deductive answers you'd expect. Like if Sharon was in Jerusalem pretty much all of 2005 and Condi Rice was there for 10 days during February of 2005, then yes, they must have been in the same city for at least a few days during that month of that year. And then other pieces of knowledge would tell you that people with their respective positions would surely meet, even if there was no news story to that effect. Lots of senses of physical containment. So you want to be able to answer questions like, is the Sonora Desert part of the sum of California, Arizona, and Mexico? Actually, the answer there is yes, and so on. Dozens of senses of physical containment. And if you don't distinguish these dozens of meanings of in, if you just use the word in, because in English we just use the word in, then you will get some questions wrong that you otherwise would get right. Even things like whether something is nailed into the wall or screwed into the wall, you get the answer wrong of what will happen if I pull this off the wall. So slowly we've had to add metaphysical distinctions that are not captured linguistically. Of course, you can express them in phrases and sentences in English, but they happen not to be captured in a single English word or a single Japanese or Chinese word, but still they've turned out to be useful. And so that's why the number of predicates even in our system is fairly large. Over 10,000 types of events, ranging from things like giving somebody something, to pumping fluid, to thinking, and so on. 400 ways of relating a participant in an event to that event, like something that's created during an event, or somebody who did the event, or something like that. Lots of ways of talking about emotions and contradictory emotions and what led to various emotions and what the impact of having an emotion is, and so on. Lots of propositional attitudes like knowing, dreading, believing, desiring, perceiving, and so on. All these are modal. They go beyond first-order logic. And so again, kicking and screaming, we had to extend our representation language to second-order and then eventually nth-order predicate calculus, because otherwise there are just lots of things that you can't express that you need to express because human beings deal with this, like Israel wants Egypt to believe that the United States would never ... You have to be able to communicate and represent those, and if you can't, then your language is only going to represent a fraction of what human beings know and communicate with each other. thousands of kinds of devices of various kind and device predicates and so on. So basically the question is, how are we going to build this? We started in 1984. Originally my work in the 70s dealt with things like machine learning. The trouble with machine learning is, well, one of the good properties seemed to be that learning occurred at the fringe of what you already knew. So you learn some new thing is similar to what you know already, and here are the differences. So you could learn things that were one step away from what you already knew. So the more you know, the more rapidly you can learn. But unfortunately, if you're way over here on the x-axis, you're way over here on the y-axis. And a lot of our learning programs were there 40 years ago. A lot of our learning programs are still there today. They don't know much. They can't learn much. To the extent that they appear to learn, they're largely either doing statistical parameter fitting, which of course is extremely useful, but limited in terms of what you can learn, or they're discharging potential energy that was stored in them by their creators. And since I wrote a lot of those learning programs, I'll say unconsciously stored in them by their creators. Potential energy in the form of a judicious representation to use, a perfect set of training data to give the system, a perfect choice of what variables to pay attention to, and so on. If Kepler had had this little table of 9, or I guess in his day, 5 pairs of numbers, he would have come up with Kepler's law in an afternoon rather than in a lifetime. So you get the appearance of learning without really deeply learning if you try this approach. And over again, people who've tried to learn from scratch, to get programs to evolve and so on, have run into this problem. You're able to get parameterized learning of what you already know, but it's very hard to get the system to take off unless it already knows an enormous amount about the world. So we have to prime the pump. So then we thought, well, we could get the system to understand English, to understand and process language, then we could just read all the online material. And even in the early 80s, we believed that something like the web would be coming and there would be massive amounts of online material to read. But if you remember all those examples I gave you about why natural language understanding was so hard, basically you have to already have a lot of common sense in order to benefit from reading natural language, except in isolated ways, which we'll see in a little bit. So the sad realization we came to in the early 80s was to get the knowledge primed, to actually build enough of this in, to prime the pump, we'd have to manually add pieces of information one after another to the system till we got enough in there that we could get natural language understanding, till we could get automatic learning to take place. So the calculation we did on the back of an envelope, actually Minsky insisted on an actual envelope so he could do the calculation on the back of it, was that on the order of a person millennium of effort is what it would take. And just about this time, Admiral Bobby Inman came to see me. I was a professor at Stanford, and he basically said, look, you've got like half a dozen graduate students here. You do the math. If you're really serious about this, you could work for 200 years and maybe get this done, or you could move to the wilds of Austin, Texas, have 50 people or 100 people work on this and live to see the end of it. So it was a close decision, but I ended up deciding to move to Texas. To make a long story short, that's basically what we did. So we spent 10 years at MCC getting this pump primed. We spent the last 12 years as a separate spin-out company called SciCorp, continuing to do that. To make a long story short, after a couple decades of working on it, we got close enough to this crossover point where nowadays most of the activity that we do in our company is not this manual monks in cloisters scribing on illuminated manuscripts to add the 3,000,007th piece of information, but rather learning by automatically extracting information from the web and extracting it in many cases from natural language on the web. To give you an example of how we do that, and this is stuff that was motivated by Peter Norvig and some other folks, and again, you probably know the history of all this better than I do, but basically, every time you have an organization, for instance, Abu Sayyaf, there are 100 things you want to know about it. Who are its leaders? Where was its headquarters? When was it founded? And so on. For each of those, we have various ways of generating some English sentence fragments that would basically be a way of saying, in this case, when the organization was founded. So you simply hand this to Google and you get your answer. In this case, you get something that says in the early 1990s, and we have a way of representing the early 1990s. Some other source might actually have a date. Various sources might have conflicting dates and so on. So not all the information you get this way is reliable. In fact, only about 50% of it is reliable. Here's another example for the height of the Eiffel Tower, where basically you have various ways of fishing for this. In case you wonder why there's only 50% reliability, well, why does it say the height of the Eiffel Tower is 36 feet? It's basically because if you go there, the very first hit that Google gives you says, the height of the Eiffel Tower is 36 feet. Now, it continues on after that, but still, if you just read the first part of the sentence, you'd get the wrong answer there. The cross-out line basically means Cyc using knowledge of monuments and towers to know that 36 feet is probably the wrong answer and hundreds of feet is probably the right answer. Here's another case where there's not a single marital status, but there's a small number, like half a dozen different marital statuses. So for each one of those marital statuses, you do what we just said. And in this case, in the case to see if he's married, you generate various things like this, and you find out, yes, something talks about his wife, and so he's probably married, and so on. So we did some experiments about 5 years ago for could we actually populate Cyc's knowledge base by doing this kind of fishing on the web? And we basically found that the answer was, by and large, yes. For various kinds of predicates, you could get fairly high rates of success. So remember, what we're talking about is translating from Cyc's formal predicate calculus language to various English forms, handing those English forms to search engines. Sometimes we use AltaVista because it allows us to put in even longer queries character-wise than Google does. Then, based on the results from that, translate those back into predicate calculus. We were able to get hundreds of ground atomic formulas, ones that don't involve variables, per hour that way, which is pretty exciting. In case you wonder why it's not, again, 100% accurate in this, like the hats worn on head, it turns out if you look through the top, whatever it is, 10 or 20 hits, about half of these aren't hat on head, they're hat on something else, like hat on nose or hat on legs or something. And that actually goes back to one of Peter's examples, actually, about water flowing downhill. It turns out because most people in the real world know that water flows downhill, if you look on the web, an awful lot of the expressions on the web are water flowing uphill used for metaphorical effect. And so the web is written for people who already know that water flows downhill, and it's like confusing or stupid or bizarre to actually say that in writing. And so if you're not careful, you end up getting this sort of 50% hit rate, 50% error rate. So what are we going to do about that? What we decided we would do is take the Cyc-L that got produced, generate alternate paraphrases in English, generate different ways of saying those same things in English, negate half of those, hand that to novices, tell the novices, these web volunteers, that they're playing a game, a matching game, very similar to the ESP game that CMU has come out with for captioning images. If you go to our website, you can actually play the game, and afterwards I can show you a live demo of it. I did bring a few PowerPoint slides in case something went wrong, so I'll show you a few PowerPoint slides. But basically, the people who play the game are told things like, the act of clenching one's fist expresses frustration, and they can agree with that or not agree with that or whatever, and if enough people agree with it, then the system believes that. And half the people were told that it expressed something else, just to make sure that we're not putting in stuff that people just say yes to all the time. And sometimes there are order of magnitude questions like this, like what's the rough order of magnitude of size of most liquid products? Atom-sized or whale-sized or shoebox-sized or something like that. And once we know a whole bunch of things which are shoebox-sized, then pairwise we can ask volunteers which of them is bigger than which other, and so on. So you sort of get the basic idea. Because Cyc has no actual taboos, it occasionally asks you questions that are like embarrassing, but you win some, you lose some. This is actually a reasonable question, even if it's a little bit embarrassing. So to get the basic idea. So there's a kind of apparent conflict, paradox between what needs to be shared if you're really going to have this semantic understanding and the fact that there is no correct ontology. So this is actually the beginning of the summary, so I'll try to wrap up in the next 5 minutes or so. So what needs to be shared, over the course of the last 5 decades, people have slowly moved down this list. A lot of the semantic web people still believe that something like sharing XML bags of keywords or XML terms is going to be enough. The trouble is that 12 different sites will differ on what the meaning of an employee is, or what the meaning of a company vehicle is, or what the meaning of a holiday is. And so if you're not careful, you have the appearance of understanding without real understanding. If all you're doing is trying to find relevant pages, that's not so much of an impediment. But if you're trying to answer arithmetic or logical questions by combining information, then small errors magnify as you combine the information to actually get the answer for the user. So you really need to share content, and you need to share not just the meaning of the terms, but the context in which various things were said. Who believed this? When was it true? At what level of granularity was it true? And so on. So if you're not careful, if you just look at something like RDF, you have a handful of relations. Even something like DAML, OIL, AL, you have tens of relations. What we've found is that you need tens of thousands of different relations to really capture the nuances that will keep you from making those sort of brittleness errors. You could think of this as the analog of why do we have more than 5 or 50 words in English? Basically because if you try to limit yourself to that small a vocabulary, there's going to be an awful lot of misunderstanding among human beings. When I say there's no correct ontology, I mean things like our poinsettias red flowers. Well, it turns out they're not really flowers at all. But if your spouse asks you to pick up those red flowers that he or she likes, and you come home and you don't have them, and you say, I didn't pick them up because what you like are poinsettias and poinsettias aren't flowers, that's not a good thing to do. It's not a good strategy. So there is an ontology of like survival in everyday marriage, for instance, in which you damn right poinsettias are red flowers. And there's an ontology in which apes are monkeys, and an ontology in which monkeys are apes, and so on. So basically, this is where contexts come in, where in one context, one generalization relationship holds, in another context, the converse or no relationship holds. So you really need to divide your knowledge base up into locally consistent contexts, much the same way that the Earth is locally flat. Even though you know that it's globally round and spherical, you act as though it were flat, and that's okay because it is locally flat. In much the same way, our inference engine acts as though our knowledge base were consistent, and that's okay because it's locally consistent. I'm going to skip this issue, but basically, there's no correct knowledge base. Facts that are believed at one time or by one person. Even things like if it's raining, you should carry an umbrella, which you might think is pretty uncontroversial. Well, that's really only true if we're talking about human beings after the invention of the umbrella, and not if you're about to like go swimming, and not if you're someone who is basically dying of thirst, and things like that. So each assertion has to be put in the proper context, and by now we've identified about a dozen different facets or attributes or dimensions of context space or microtheory space. And I won't go into them here, but I have a long article about this if any of you are interested in that. And there are various calculi for the system automatically deciding things, when you can consider if you've got a piece of Pennsylvania and a piece of 1985, is this statement still true? Well, yes, in this case, Thornburg is still governor and Reagan is still president, but if we had said things like there are 900,000 doctors in the US, it's not true that there are 900,000 doctors in Lehigh County in February of 1985. So you have to be able to know when you can and can't do these sorts of conclusions. Like, just because I'm talking from 1 to 2 doesn't mean that I'm talking at any particular second. Well, it may seem that way, but not at every single second during this hour. So there's sort of a complicated question of if P is true in one context and P implies Q is true in another context, in what context can you validly infer Q? And that turns out to be a very complicated question. And we're slowly making progress on the system automatically being able to answer that. So how do people harness our system? They extend the ontology, they add new vocabulary terms, they add new assertions, in many cases using those new terms. In very rare cases, they have to add new reasoning mechanisms to the set of 1,000 heuristic level mechanisms that we've got. At another level, what people are doing is making use of our ontology, which we've made available for free, even for commercial use for anyone who wants to use it. Or they're also using the entire knowledge base of the several million assertions involving those terms, which we've made available for free for R&D purposes for anyone who is interested. So if any of you are interested, we encourage you to make use of ResearchPsych in your R&D projects. And if you have the time and want to play that factory game as one of our volunteers, you're more than welcome to do that. So OpenPsych contains about 1 million assertions, even though it mostly contains the hundreds of thousands of concepts. Just the simple taxonomic assertions it contains are on the order of about 1 million. ResearchPsych pretty much contains the other couple million assertions. We have a moderate number, even though we haven't been advertising this in a big way. We already have 100,000 people using OpenPsych in various ways, and almost 100 different groups around the world who are using ResearchPsych for various purposes. So summary was, I showed you some examples of questions that are just sort of heartbreaking in the sense that Google can almost but not quite answer these questions. The final arithmetic or logical step still has to be done by a human being. That we could semantically break that bottleneck if we could get the system to even partially understand the queries and the content. And that you can do that by priming the pump, getting enough knowledge in there that the automatic mechanisms that you guys are all interested in doing could use that as grist, could use that as a starting base to rule out statistically implausible and semantically implausible conclusions that were gotten by the learning process. So we pretty much have primed that pump over the last 22 years, and we're now at the point where we're focusing on that kind of learning and knowledge acquisition. We look forward to working with any of you who are interested to help accelerate this process so that we can achieve Sergey's goal of general AI by 2020. Thank you. So I'll take a few questions that all folks have, and those of you who want to see some of this stuff live on a very small screen, come on up. And actually, we can try again to get it to project, because using the washer repairman heuristic, this time it'll work. Yes?
Have you tried identifying children's programs like Sesame Street where they don't typically talk about water or milk pillars?
Yeah, so our original plan in 1984 involved an awful lot of human subjects work with young children and so on, looking at children's books, looking at the why, I'm trying to remember what it's called, not Why We Learn, it's Why It's True or something, series of books for kids and so on. And basically what we found, to our chagrin, was that reading children's stories and talking to children was in many ways linguistically just as complicated as reading adult stories. And there are all sorts of additional complications, like for no reason that we could tell in children's stories, it's okay for animals to talk with no explanation. But it's not okay for animals to fly with no explanation. You know, it's like, you know, what the hell? So it basically became more complicated. And if you look, they're just very, very metaphor-laden. In fact, if anything, children's books and children's science books and so on are even more laden and riddled with metaphors and analogies to try to reach kids than college textbooks on the same subjects and so on. So somewhat grumblingly, we were forced to sort of cut back on that kind of work. However, one of the things we do is to constantly ask our people to come up with these common sense tests. Remember I said we had this large library of common sense tests that we're constantly asking the system as a way of measuring progress. And a lot of those common sense tests are what's something that you noticed your kid saying the other day that caused you to realize your kid knew something, and see if psych knows that thing. So we definitely are interested in what kids know. It's just that many of the structured programming, structured content like Sesame Street and so on is something that it's going to take psych plus additional knowledge in order to really make effective use of. Yes, well, you can infer the question from that answer, but I will repeat the question next time. Other questions? Yes.
You didn't talk a lot about prediction in these artificial intelligence systems. I mean, there's a lot of slides that want to, does this terrorist have a wife, or where did this event occur, things like that. But what about, say, a question of like, when will the virus, the influenza virus, mutate? And like, from all the
yeah, so that's a good question. At one level, I basically want to tell you that in order to do a good job of that, we would have to do a vastly better job of integrating probabilistic or uncertain reasoning with the kind of logical inference that we do. So having said that, and by the way, we keep waiting for someone to do that. So 5 years ago, we were waiting for Daphne Koller to do that. We're still waiting, and we're still following folks who are doing that. Michael, you're just waiting to tell us.
Well, we're actually, we have some research projects where we're working with people.
Yeah. Yeah, so I was going to, okay, so that was the next thing I was going to mention, which is having said that we can't do that, yes, under the covers slightly, we're starting to work on little projects to try and do some of that. And in some cases, we're able to come up with fairly provocative scenarios, abductively, of essentially terrorist threats that the government should be watching out for. Not so much working out the third or fifth decimal digit probability, or even the first decimal digit probability, but still coming up with things that are likely enough that it's worth a human worrying about this or that particular scenario. So we're just at the stage of grappling with this issue. And I look forward to the day when all of the issues that we're grappling with are sort of at this level, rather than the kind of slowly pulling the system from idiot savant to enough of a kind of a artificial but still ignorant human being that it makes sense to try to get that next level of education done.
So that's it. There are some things you can do.
Michael, do you want to come and use the microphone? This is Michael Whitbrock, who's our VP of Research.
So that said, there are some things that you can do with purely deductive reasoning for prediction. So for example, psych contains a large number of event types. So things like what goes on in a kidnapping. And one thing that we've got, in fact, several projects, both in the past and ongoing at the moment with the government, is trying to do that sort of event recognition. So if you've got some idea, you've got some indication that you've got some sort of event going on, you can then take the roles which are instantiated in the event which has happened so far and use those to predict what's likely to happen in the future. And that is something that you can do usefully with purely deductive reasoning. You can do even better at it, we think, if you're able to do probabilistic reasoning, especially with respect to recognizing what event types are probably going on.
One other example of that is if you have a comprehensive knowledge base, you can do reliable statistics based on that. So one of the largest contracts we actually have gotten was from the Department of Defense to build up a large terrorism database, large terrorism knowledge base in psych. And so you can basically, once it's complete, you can already do this, but not as accurately. You can ask questions like, in cases in the last 15 years when Hamas has abducted someone and ended up killing them, what was the number of hours or days between the event and the killing? And if you have a complete database, it's not rocket science to answer a question like that. So based on that, you can begin to make quantitative predictions about the future and so on.
Sort of evil purposes. So can Google, but it seems like that yours is a little bit more directed, right? Because I mean, if I wanted to go to Google and say, tell me a city that has lots of birds and few hospital beds, it would be a lot of work. Seems like it would be a lot easier, and I'm not sure if there's a good answer to that question. The second question, which you can also address, is I noticed that you had a like some sort of product that you were pitching for sort of security called like Secure Psych or Open Secure Psych or something like that, and I wondered if you could tell us about that.
Okay, so I don't have a great answer, although I have an answer, for the can this be used for evil? It's a kind of radar gun, radar detector situation where, of course, the technology can be used for ill as well as for good. If you look back to electricity or almost any power source, the same thing can be said for them. In fact, the first the first commercial application of electricity, the contract that was fought over bitterly by both Westinghouse and Edison, was for the electric chair. And when Westinghouse won that contract, Edison for many years tried to get the verb to Westinghouse to mean to kill by electrocution. But yes, of course, any power source can be misused. But by and large, the U.S. government is much better funded and much better informed than the terrorists. And I'd much rather see these tools in the hands of people working to safeguard this, because basically, yes, it may take the terrorists 15 minutes to answer the question of cities that are warm enough and have enough animals and so on, using only Google. But they're going to spend the 15 minutes. And so given that they're going to be getting these answers anyway, I don't think we should apply the kind of ostrich head in the sand approach of let's not develop the technology because it could be used for ill. I think overall, if you think about what artificial intelligence could bring to the world, it's a kind of amplification of the human mind in much the same way that physics and engineering has amplified our physical selves to enable us to do a lot more than our muscles can in terms of how far and how fast we can travel and how far we can shout to another human being and so on. In much the same way that biology and medicine amplify our physiological selves so we live longer, less disease-ridden lives. So that kind of mental amplification would allow people to misunderstand each other less by doing a better job at machine translation, for example, and real-time translation. Would enable people to be more creative, to search deeper, to search faster, to do more things in parallel. And if we as individuals are smarter, then I believe it's going to follow that we as a species are going to become smarter. And if you look back historically at when the last time was that our species got qualitatively smarter that way, you probably have to go all the way back to the creation of language and say, well, just like we look at the pre-linguistic cavemen and say they weren't quite human, were they? I think in the distant future, people will look back at us at this very moment in time and say they weren't quite human, were they? Then in terms of your second question, as far as Cyc Secure, one of the commercial applications that we're trying to push, not actually getting commercialized, but we'd like to see it commercialized, is using Cyc to come up with attack plans and defense plans that would work against and defend your, for a particular network. So here's a plan that's a 30 or 40 or 50 step plan that would only idiosyncratically work on your network, and it only works because this person takes their lunch hour at a certain time, and these three machines are near each other physically, and so on, and maybe it involves real world steps like calling in a false fire alarm and who knows what. So basically used Cic's knowledge base and used just plain old AI planning to come up with attack plans and defense plans using something like BugTrack, DoD CERT, and so on as the 0th level plans for what are the 0th level ways of causing problems or having vulnerabilities in known commercial pieces of software out there, and having an ontology which we have of different kinds of attacks and different kinds of mischief and harm that people can cause to a website or to a company.
So with respect to Cyc Secure, in particular,
do you want to use the microphone?
The reason that hasn't been commercialized is due to a lot of very silly other people's startups failing sorts of reasons, and we would very much like to, for example, have a good network testbed to try and push that forward again. So do contact either Doug or me about that, and we can give you all sorts of information about Cyc Secure and talk more about how it might be useful.
Yes, I didn't want to do any finger pointing, but basically that's what happened, which was an undercapitalized company that tried to commercialize it, failed, and now we're back to starting to commercialize it once again.
One way you might gain capital for that, given the thing about the whole plot of when it ends up someone taking a particular lunch hour, etc. Have you thought about selling that to, say, the next Mission Impossible script? But three more serious questions.
We have actually had one X-Files based on our stuff.
Okay. Three questions, if possible, some of which are related. What's the speed performance?
Sorry, you're breaking up. that was a joke.
Okay.
In the case of the stuff we did for Hotbot, we had to perform in something like a 40th of a second, and that involved caching tables of information from the system so that we could do a good enough job in a small enough piece of time. And similarly, we have some other applications that we're working on right now that require that sort of sub-second response time. For some of the complicated queries that I showed you, typically 2 or 3 second response time is considered adequate, but we haven't ever really pushed too hard on that. The good news from your point of view is that we just got a contract from the U.S. government specifically to speed up inference in large knowledge-based systems. And so over the next year, we'll be having some workshops with researchers around the world like Andrei Voronkov and so on, Jeff Sutcliffe and so on, to try to bring some of these techniques together and to try to harness some of their theorem provers to try to speed up by at least 1 or 2 orders of magnitude the way inference is getting done. A second thing to remember is that you really have to continue believing in Moore's law, at least for the next several years. And so something that's a few times too slow right now won't be a few times too slow in the future. And all this is without parallelism. So if we had 17,000 machines working at once, I bet we could do a lot better than if we just had one machine, especially one little, 1 pound laptop working for 2 seconds. But
No
Michael's
idea where
probably
you'd be
got
able
his
to
own
find
answer
that.
to this.
So if you look at problems like those ones answering what terrorist events happened in this location, carried out by this organization against that sort of target, those generally answer in somewhere between 10 and 100 milliseconds. There are some which take very much longer than that. There are some which take less time than that. I think across the KB content tests, which is this large corpus of test queries, the average time to first answer for them is around a second at the moment, and it's going down. So it's slower than we would like it to be, especially since we'd like to be able to solve complicated questions which require deep inference, but it's not unusable for many applications.
Mm-hmm.
Right, and I was about to say there are a lot of applications where a delay of a second or 2 is perfectly acceptable, especially if you're getting a qualitatively better answer than you otherwise would.
The other two are, I guess, sort of related. I guess they sort of tie into reflection or meta information. How knowledgeable is Psych about knowing when it doesn't know the answer or can't come up with it? I guess this would tie into how it's learning from reading the web and the like, but just in a general sense. But also, you mentioned the context of, say, Pennsylvania in 1995. How knowledgeable or aware of it would it be for dealing with a fairly dynamic situation where things are constantly changing, like the position of the attacker is here, now 1 second later the position of the attacker is here, etc.
A lot of our applications actually are of exactly that sort of nature of course of action analysis and battlefield awareness and things like that, where the situation is rapidly changing. And so we do have to represent dynamic situations, snapshots, and 4-dimensional time-space worms of situations changing and so on. In terms of Psych's knowledge of its own knowledge base, I would say it has excellent ability to represent all of that and mediocre coverage in terms of what it actually does currently represent. But there's no reason why the system itself can't automatically learn a lot of that material on its own by trying these questions systematically and recording what kinds of questions it does and doesn't seem able to answer.
So in fact, in terms of driving usability, we're talking about the answer time, that sometimes it takes a long time to answer questions even when the system doesn't know the answer. So one way that we're trying to improve usability with respect to that is you can usually do some queries of the type which Psych can answer very quickly, which allow it to work out whether it's likely to have an answer or not. So in our interfaces, we try to reflect the system's estimate of the likelihood that it will be able to answer a question of the sort that you're formulating before you get to the end and answer it. So it's so we realize that this notion of knowing what you know and knowing whether you can answer a question is very important for the types of question answering that people do. This is a very important facility that human beings have, and we're trying to work out how to do that inside a logical system. And we've got some approaches to it, but we don't have a complete solution yet.
Right, and some of the common sense tests are things like, at this very moment that you're running the test, is George W. Bush inhaling or exhaling? And of course the right answer is, I don't know. And any other answer is, in some sense, the wrong answer. So there are tests like that which basically depend on the right answer being the system should know that it doesn't know enough to answer this question. It should know that really, really quickly. Take maybe one more question and then call it quits for this large assemblage. But as I said, I welcome you to come up and take a look at the system actually running. Yes, please.
Is there a public web interface that we can play with? That gives some common sense.
No, we don't have a. The question was is there an interface where people can actually type in questions to the system? So we don't have something like that yet, but we're slowly inching in that direction, and I'd like to. I'd like to believe that in less than a year we'll have some facility like that, at least in the form of structured questions, sort of like I showed you the psych analyst knowledge base, where you won't be able to have a blinking carrot and type in anything you want, but you'll be able to have fragments of queries and fill in the blank fragments and so on. And by pulling those together and filling in the blanks, there's a truly astronomical number of queries you will be able to ask, and then have the system go off and work on those queries. Well, let me stop at this point and thank you all again. It's been great being here, and I hope to talk to some of you in the coming hour. Thank you.